Hello and welcome to this course on AI. If you're watching this, you're familiar with AI and the leading technology, LLMs, and you have an idea probably of all the design decisions that come to building systems that may use of large language models in practice in real life. So the challenge we are addressing today is how do we make sure that LLMs have access to a certain context, a certain background, a certain source of information. Let's say you have your files, could be PDFs, could be text, could be records, could be databases, and you want that to serve as a basis for what an LLM uses to reason. How do you achieve that in practice? Now, the leading technique to achieve that is what's called RAG, R-A-G, for Retrieval Augmented Generation. It's simply a set of techniques that allows us to do just that, to provide context to an LLM. Now, the point of this course today is to see how that's actually done in practice. How do you go about building a RAG pipeline? How do you go about making sure that works? And we are going to answer that question with an application in LangChain. LangChain is simply the leading framework in the space, and in this course we will actually build a LangChain pipeline. So here again, I am Harry Camden. I am a trained engineer. I've worked at places like Google, OpenAI, Amazon. I've actually built AI models, trained them, fine-tuned them, deployed them, productionized them, and I know what it takes to make an LLM product actually available to customers. And I believe that learning how RAG works is essential in creating value for your users, for your customers. Now, this presentation will be very hands-on. We will start with a set of slides which describe RAG, and which really explain all the trade-offs. And after looking at that, we will have a hands-on demo, so there will be Python code. You don't need to be very advanced. You just need some basic Python skills to follow along. And once we've done that Python code, we will then come back to discuss what we've learned, and if possible, if we're live, we'll do a Q&A session. Now, without further ado, let's dig right in. Okay, so the first step is to define our learning objectives. So the point of this course is simply to really understand RAG, really understand what the technique entails, what are the trade-offs, and how it works under the hood, to get you to be able to build an actual RAG pipeline with LangChain, and finally to go through the process of deploying such a RAG agent. Like, what does it mean to make that RAG pipeline available to users online or on your website or whatnot? So, what is RAG? So, again, LLMs have a limited context window. So, depending on the vendor, it can go up to 1 million tokens, which is impressive, a few million, but still, you cannot fit in the whole internet in the current working knowledge of an LLM. So RAG is a technique which allows you to provide up-to-date and very specific knowledge. Like, if I want a lawyer bot, I want it to feed it specific case data at the moment that I want it to reason on, right? So RAG allows me to provide very recent data, very specific to what I need the LLM to do, in a way that could not fit, like I couldn't fit the whole world's information in an LLM's working memory. And a second advantage is that by providing this specific and targeted data, you are grounding the LLM. So by providing very specific data, you stop the LLM from going into hallucinations, where pretty much the model just invents facts which sound plausible. That's a known defect of LLMs. But by providing the exact sources at the moment of inference, you reduce chances for the LLM to go into hallucinations. And so, as I said earlier, the use cases for this technique is cases of documentation search, support bots. It can be an LLM lawyer, anywhere that you need specific and up-to-date knowledge, and you want to avoid the LLM doing generalization on its memory, which will be hallucination. That is where RAG is essential. And so that's what's important to pretty much any real world use case of LLMs. Now, at a high level, how does RAG look like? So pretty much, uh, RAG works on, I would say, in two phases. First, there will be document ingestion. So you would gather your data and you will do ingestion. So you would prepare the data, clean it up, chunk it into um, uh, bite-sized units of meaning. We'll get back to it later. Put it into a database which represents that meaning in a way that an LLM can understand. That's what's called embedding. And that embedding, which represents the meaning, you will fit it into a vector database, which will store that meaning in a graphical way, which we will get back to. Don't worry about that. So that's the first layer, document ingestion. So that's how you're preparing the document to be used by your system. And now after that, at inference time, when you get a user query, what happens is the system retrieves the relevant chunks of data, the chunks we created earlier. It retrieves them from memory based on the meaning which has been expressed in the vector database. And using those chunks of memory, it presents those elements of data which are relevant to the question at hand. It presents that to the LLM at inference time. So the LLM is able to make an informed response based on information found in the database, which is just extracted. So that is what's called RAG in a nutshell. So now that we have a big picture idea, let's try to look at how a RAG pipeline is actually built. What is it made up of? So at the top of the line, you have LangChain. LangChain just provides that framework which allows it to be like the middleman, which contacts the LLM, contacts the memory layer, contacts the vector space, everything. So it's essential right here. Okay. Then you have the embeddings. So there's tools that build these embeddings, and there's a vast array of those tools. You can get some from OpenAI, from Hugging Face, which are very generalistic, or you can get more specialized ones from a very wide number of sources. But the job of these tools is to convert any piece of meaning, that could be a string of text or document, convert that into a numeric representation of the meaning in that content. So that's extremely important, to go from content to a numeric representation. Remember, computers work only with numbers. So the next step, and that's the next major component, is the vector database. Now that I have my embeddings, which are just a set of numbers, I use the vector database to store them in a way that makes it easy to retrieve the meaning later. And how do vector databases achieve that? You have to picture them like a virtual n-dimensional space where those vectors you obtain from embeddings are stored, and they're stored in such a way that you can pinpoint an element of meaning and easily identify those neighboring chunks of data which are close in meaning to it. So that's the whole point of a vector database. And the two big names I would suggest to you here are FACE, which is Facebook AI semantic search, and Chroma. So FACE has this advantage that it's really fine-tuned for speed. It works with GPUs. It's really good for when you're deploying and all that, and you really care about speed. Chroma is more adapted to interfacing with Python code, so that can be good in like in a development setting and when you're experimenting, as well as simply PostgreSDB. You can have a vector column, which is good enough for experimenting and when you're starting out. So now that you have LangChain, which is kind of operating behind the scenes, you have the embedding toolkits which converts it into meaning, you have the vector database that stores that meaning. You now take all of that and you bring all that meaning to the model, which now uses the content you've extracted to reason. So these are all the components that work together to make a RAG pipeline come to life. Now let's look a little bit more at what it means to prepare data. So preparing the data is a process in which you make forms of data which are disorganized, which have their own idiosyncrasies, and you try to standardize them in a way that's fit for your use. So your data preparation pipeline will really depend on the system you're trying to build, and it will never be the same as another person's, right? So the first thing you do is you load the source, you obtain the data, you do the database query, you obtain the data. The next thing is to clean that text and normalize it. So make sure it uses uh, the same encoding format, right? Is it ASCII? Is it UTF? Are you taking sentences? Are you throwing away emojis? So you need to clean up your content and bring it to a certain standard which you have defined. The next step is to chunk it. So you want to break down. So if I have a whole wall of text or a whole document, I need to break it down into chunks, which allow me to better extract the meaning. And typically those chunks have overlaps. That's just a way to ensure that no meaning is lost. So if I have a chunk, let's say I have a 100 sentence word, I will not break it down into 50 and 50, right? I may break it down into 60 and 60 in such a way that there's a 10 word overlap between chunk 1 and chunk 2, and that allows me to better extract meaning from those from my source data. So once I've loaded my data, cleaned it up, prepared it, sanitized it, broken it into chunks which have some minor overlap, then I put it through the embedding system to get that vector of numbers, which I then put into my vector database. So that is the whole data preparation step that happens before when you're getting a RAG pipeline set up, and you need to be able to automate this to a certain degree, where when new data is available, it goes through this pipeline and finds itself in the vector DB. So now, let's have a look at what happens at the level of the vector DB. So now that we have our embeddings, which are stored like vectors within the vector DB, what happens is at the moment of inference, we use what the user is presenting or any other information to go into the vector database to retrieve similar data, right? So we do a similarity search, which allows us to surface data which is relevant. So if a user is talking to us about phones, our similarity search may find articles about tablets or about phone plans, anything that may be similar to what our target, our end user is talking about. And that's the point of similarity search. So again, we talked about vector databases like Face and Chroma and all that. And what they do is they pretty much feed off of what is happening in the conversation right now to go into the database and see pieces of information that may be relevant, which they would then extract to bring back to the attention of the LLM. And the key parameters that you would have to juggle with here are top K and exactly what embedding model you use. So top K simply means how many results do I want, right? So as the conversation at the level of the LLM progresses with the user, and at every step I go back to the vector database to extract similar pieces of information which may be relevant. How much information do I need? Like if I go back to the database and I query too much information, I run the risk of losing like the value of the RAG, which allows me to be specific. Like if I just go in and I try to draw in too much information, I may pull in a lot of irrelevant information, and I may be incurring a lot of database costs to an LLM cost to process all of the data. But then again, if my top K is small, then I may not get all the information I need to give a meaningful answer to the user. So this top K variable is something you want to experiment with to see what works for you. Top K again is just what is the number of relevant of similar results I want to extract from the vector database at each round. So you're going to want to have to experiment with different values of top K, right? Not too broad, not too small. And then also the embedding model you use, right? So as you are experimenting with your RAG pipeline, you may discover that the embedding model you use, you may be discovering that it doesn't surface things which are relevant in the way that you desire, right? It may be sticking to sticking to categories that you don't really care about, right? So you want an embedding model that really surfaces the meanings that you care about in each piece of text. So you want to, as you deploy a RAG pipeline, you want to explore the effect of changing the top K variable, but also sometimes of swapping out the embedding model. So that's what you would do at the moment you're setting that up. So now let's do a quick live demo on building an LLM, a RAG pipeline. So the goal would be to actually um, have that pipeline running, have a vector store that we will load a PDF file in, and try a conversational interaction with the AI. So let's do that and come back. Here we are for the hands-on demo. So what we're going to do here is to actually build a RAG pipeline using LangChain. And I had to redo this section because since AI moves so fast, the different packages tend to change a lot over time. So you need to update your code if you want it to work with the latest versions. So this code right now will work with the latest versions of all these requirements as of December 2025. Okay, so without further much ado, let's get going. The first step is to install the requirements, obviously. So we're talking about LangChain OpenAI to interface with OpenAI, LangChain community, that's helper functions, the text feeders, which allow us to do the chunking, Face, that's Facebook AI semantic search. I'm using the CPU version here, so it's compatible, but if your machine has GPU, like right here, you could use Face GPU, and then PyPDF to interface Python and PDF, pretty much. Let's go. So within the Python code, the first thing you would do is to make sure that your API key for OpenAI is available in the environment variables. I do that here in this fashion, but you're never supposed to put API keys in production code because that's leaking secrets and that's really no. But since it's just demo, let's do it right away. So again, importing the PDF loader, the text editor, the embeddings tool, which creates the embeddings, very important, Face, and also special mention right here because LangChain, the big value of LangChain is that it creates kind of a predictable, stable interface with how you interact with these LLMs, which are just like stateless machines, right? And a big way it does that is by using this module, is by using this object called chat prompt template. Pretty much it allows you to create like a stable, solid interface which kind of gives you structure you can build code upon. So runnable pass-through is just a pass-through function, no actual great value there. So the first thing I would do, you should do in your system is just to check that the API key is available. That should pass. That's an easy pass. Now let's look at our ingestion pipeline to the RAG. So RAG, retrieval augmentation declaration, you need to first ingest data before you can use that, right? So here what we're doing in this demo, we are just using a PDF file, but that could be something else for you. So please adapt accordingly. So since I'm on Colab, I uploaded a sample doc right here. So the sample doc was created just for this demo. So it's a sample doc that I created, which talks about a tool called Atlas, which I just generated like that. Doesn't really mean anything. And so what I do with the sample doc is I load it and then I build a splitter for it. So this object called a splitter, its job is just to take a bunch of PDF files or a bunch of whatever and text and then split it in a way that is conducive for a RAG pipeline. So this is what happens here. It's chunk size, chunk overlap. We set it up, we get the splitter, and it breaks it into chunks. That's important. Once it does that, perfect. The next step now, we have this chunks, so we need to convert them into a series of numbers through embeddings and then get those numbers into a vector store, vector database. And this is what we're doing here. So we're using OpenAI embeddings. There's probably others and all that, but we're using OpenAI embeddings and we are storing them in a face a vector DB pretty much. So this code has stored the meaning of the text we're trying to find into this vector store pretty much. So now let's build a little retriever whose job will be to go into that vector store and get us the content we need. This is what we do right here. So we create a retriever which searches by similarity and tries to extract the the four most similar documents in the vector store. So what we and then we just put it into this function just for um, I would say to provide a simple interface. So this will give you a function which you just call with a string, and that will do the search for you. So once I've run this, my vector store is ready, and the function to retrieve data from the vector store is ready. As simple as that. Now, let's go to actually building the RAG pipeline. This is where the magic happens. So I'm going to put all of what I have together into this RAG chain, pretty much. So this is the system prompt, which tells the system, "Oh, you're a helpful assistant. I want you to, provide context to the user, provide help to the user based on the context and everything. Expect to have input and blah blah blah." I define the LLMs I want to use. I want to use GPT-4o. The temperature is a parameter that allows you to tweak how variable and how unpredictable you want the output to be. And then I put all of this into my RAG chain. So my RAG chain is pretty much composed of, you see, this is the system prompt, this is the LLM, which does the reasoning, and then these are what happens at every step. So at every step, the question is a user's input. Put it to put through a pass through. No change to the user input, but give that to the system. The context. What happens to the context is the context is we take the user's question, we retrieve documents that are similar to that, and then we get the page content of those documents and we join them. So we create kind of like a blob of data, and we give that as context to the LLM to work with. That's very important. So now, what I did in number 5 here, it's a bit overkill. There's some dual code happening, and the reason is you will see as we go. So the RAG chain here is perfectly capable of asking and having like kind of follow up, like remembering the previous question. That's the whole point of LangChain. But what I do here by building my own manual chat history and having this ask function is I also want to create my own within my Python code. I want to create my own chat history because you may use something else in LangChain or anything. So I want you to have like a visual representation of what it means to have a chat history and how that can be helpful. So in this case here, when I say ask, when the ask function is run, what it does, it invokes the RAG chain with the question, and then it appends both the user's question and then the system's response within the chat history. So then you can now use this chat history as a list, which you can put in like a user interface to show your chat or whatnot. That can be useful. So now that we have a RAG chain, we have a piece of code that does the ask and stores the history in a way that's accessible to us. Let's run this thing. So the way we're running it here is just a loop which will take input, ask to the LLM, and then present the output, and we run until we call exit pretty much. So what happens here is, in addition to, because ask already uses LangChain, uses our RAG pipeline, right? So it already does a retrieval, but to have that visual representation for your interface, I'm adding another retrieval here just to show the documents that were given to the system. You do not need to do that, but I'm just adding here so we can see visually the sources that were sent to the LLM at every cycle. So I hope that's understandable, and we can run it right now. So again, this is pretty much ChatGPT, and ChatGPT has no reason to know how what is in my document that's right here. So I'm going to ask this instance a question about the document that I just put into the vector DB above. So I'm going to ask, how do you install Atlas, for example? That's just a question. So yep, see, so what has happened is it used sample.pdf, which we gave it, and it was able to answer to install Atlas, download the installer from the company portal, follow the steps, run the setup, accept license, configure the database, and start the service. Typical environment supported. And this is exactly what you'll find in this document. Right, to solve put it in configure database, typical support environment. So it just went verbatim. And so this is the power of RAG. So if I had to ask ChatGPT on the ChatGPT website, it would not have this insight that I provided, and these are the sources. Now, just to see the power of LangChain, which in the fact that it automatically handles history internally, what I would do is, hey, I'll just come and say, hey, you know what? Please, can you repeat the first step? So first step here, we're using OpenAI ChatGPT's reasoning to understand, oh, I need to find the first text. And then we base ourselves on the fact that it has access to this chat history to be able to identify what's the first step above. Let's do it. The first step to install LS is to download the installer from the company portal. Yeah, so we see it has reasoning provided by the LLM, in this case ChatGPT. It has access to docs, which is the RAG pipeline, and it has access to history, which is provided by LangChain, and which we also have made a copy of within our chat variable. So now that I've done this and I am satisfied, I can lay it to rest by quitting the loop using exit. Boom, very good. And now I'll have a look at the chat history, because we were making a copy of our chat history, and that's all the values of having your own copy is, LangChain could crash or whatnot, and you want to be able to know what happened. You want to store it in the user's profile or something, and that's what you get. User, how do you install Atlas, assistant, and it's all right here, all the history of the conversation. So pretty much what we've done right now is we've built a RAG pipeline, we've made it work, we've run it on actual data that we created from scratch, and I hope this gives you an understanding of how that works. Thank you. So let's have a little quick brush of the challenges and mitigations here. So again, LLMs are prone to hallucinations, just making up things, and it's based on just how they generalize everything. So it's very normal for an LLM to hallucinate, and we combat that by grounding, so providing data to the RAG pipeline, as well as prompting it in the system prompt to cite its sources. Then another challenge is large documents. If you have a lot of large documents that you want to use RAG with, then you have to be smart with how you do your RAG pipeline. But so here would be having a good chunking strategy, so not having chunks which are just too long, and then maybe hierarchical retrieval. So rather than having a vector database with all the chunks of all the documents, maybe you have a two-step retrieval where you first retrieve a domain, and then within that domain you retrieve a document, and that's the document you provide to the AI. So multi-step retrieval can help. Chunking the data themselves in a more smart way can help. And finally, there's a cost concern. So can you imagine every time you need to make a call to the LLM, you add the vector, you add the whole embedding, because you need to embed whatever is relevant to the conversation right now to put it into the vector space to make the research. So that adds a lot of cost in addition to the LLM cost itself, which is already high. So the solution here may be to cache. So if you have frequent requests where people bring up similar topics, and those topics need to be embedded compared to what's in the database, and retrieval happens, if you can cache that whole back and forth, then you avoid a lot of the costs linked to RAG. And also, if you can use the models which are just the right size, so avoid using models which are too big, where they will be costly, but use the models which provide the exact amount of value you need, because with RAG, you'll be using that model a little more frequently. You'll be using your input window a bit much more. You wouldn't, because you won't just be using text. You'll be using text and retrieved documents, right? So you really want to go for models which are the exact size you need and not just overkill, right? So that will allow you to limit the costs of running your LLM plus a RAG pipeline. So to wrap it up, we have talked about RAG, and we've seen how RAG grounds an LLM, and we've seen ways to pretty much make your RAG pipeline work to the best and optimize for costs and everything. And so the next course we should go for is tool invocation with an LLM, API integration, and how to deploy your LLM with tools like Streamlit. So thank you, and I hope to see you in the next courses.